Thank you very much, Fred, for the opportunity and for this nice introduction. And indeed, I'm going to share with you a little bit of the way that I think our field is evolving. So just like a bit quickly to remind you, what do we already currently have? So you saw that there are quantum links. One of the biggest one and the most expensive one is the one established by China, allow you to satellite communication, doing all of this security that you heard from Eleni Diamanti right at the beginning of the course. Then you also heard about quantum computers, some sort of NISQ computer exists. They allow you to do all of these exciting various algorithm things to do. And today you just heard from Fred that, people already in this Quantum Internet Alliance, they are putting a small quantum computer connected to each other in order to do distributed quantum computing. So my claim, the future is not in too long time, is something like this. So we're going to have a data center, exactly like the classical data center that we have. There are a bunch of computers, there is a bunch of classical computer, compiler, software stack, the usual story that forever we have had about distributed computing. You have classical link, you have quantum link, you put all of these bits and pieces together. And why do we do that? Why do we want to go there? Because now, you saw some of the example already in the earlier lecture, because we know that by doing this, putting quantum and classical and link and everything together, we can enhance efficiency of our computation, efficiency of our communication. We can enhance security as well as integrity. So I want to walk through one particular example that in this futuristic plan, which is not too far away, allows us to concretely achieve something that is not possible classically. So let's abstract it a little bit in order not to go through all the engineering part of it, and think of it like a use case that I like you to keep in your mind, and then I convince you how this use case exactly is something that we can achieve. And everybody these days talking about this privacy-preserving quantum machine learning. So if you look at already one of the hot topics, that we are in the scenario that somebody has the data, like, I don't know, Google has all the data of what you're clicking, what you're not clicking. Amazon has the data of what people are buying and what not buying. Somebody else has a super high powerful HPC who's trying to be able to manipulate. And then there is plenty of application that you want to run on those data, but now you need to also apply to the rules of the privacy of your data. Not everybody can share their data depending on the context of the data. Not everybody can trust the HPC actually doing the right computation. And not everybody knows actually the correct computation has been performed. So this topic exists already in the classical world, which is exactly secure multi-party computing. And what we're going to talk is that, okay, now we need to do quantum secure multi-party computing, because we have quantum computer, which is doing things much faster, much better. You heard about quantum machine learning from Jordanis, which is also talking about that. But we need to take into account the privacy of the data. So that's going to be our working example that we want to show that when can we have it. In order to show that, like that's the plan of the talk, so I start building all the components that allow us to achieve this wonderful use case application. So we consider the scenario like we have one honest client and one malicious server, being whoever who has these devices. And here I'm going to show you all the building blocks. So what is possible, what is not possible, to really show the difference between classical and quantum. Then the building blocks are exactly things that you have already seen. The quantum key distribution for encoding, teleportation, gate teleportation, and self-testing, which is one of the other areas that Fred has been active, and we almost worked with, which we didn't. But then, and putting all these bits and pieces together, we achieve this first protocol for universal blind computing. And then I start add things depending how much time I have. Oh, I didn't even start my time, so I have plenty of time. How much time we have, I show you that how we go towards our goal. That what if now we have a malicious client, malicious server, and this is the example, like Google wants to have the data, Amazon wants to have the click, nobody trusts each other, and they should not making sure how they can calculate this thing distributively. And here the main idea is that the beauty of this thing, well, okay, we don't need to reinvent all the wheel. We use the technique that exists in the classical scenario, and then we extend it to the quantum scenario. So that's the main message. And finally, when we go to the multi-client, multi-server, my futuristic picture, so again, we show that how we use classical technique combined with the quantum technique, and we have this hybrid thing which is achieved apart. And then I also want to say that when we can have this thing for real. Obviously, I just don't want to say that, oh, this thing could exist. Actually, most of the theme that I'm going to talk about, although it's hidden, is that I always try to make sure that we think things as practical as possible. I'm not a physicist, but I love physicists, and I work very closely with experimentalists. So we are very much aware to come up with the solution that's actually practical and is not futuristic. It's something that can be done today. So hopefully at the end, I convince you why all of this theoretical protocol that I'm presenting that actually can be achieved in not so far away. Okay, so that's the plan. Let's start. So the first scenario is that the thing that we have a client which has an algorithm, which has a particular data, and it's exactly like the normal cloud scenario that we have. And it wants to run some computation because somebody else has quantum computer. And this is very important. These quantum computers are not in any decade is going to be some quantum laptop that everybody has at their home. These are big devices sitting in the fridge. They have a special sort of manipulation. So they are very much like mainframe or HPC computation, that you have a center, hence data center, and now people want to run on computation and to look at it. And then you can ask question, okay, can I really run it on the internet, the classical internet, run the computation? And this is actually what we have. The Rigetti machine, the IBM machine, and Xanadu machine, a lot of these quantum computers are already providing access on the cloud. So you can sit down on a little laptop, write your little quantum circuit, and run your computation on top of it. Of course, the problem is that in currently available cloud access to all of this quantum computing, there is no privacy. Your data, your algorithm, your output, your result is completely public. It's even in a sense is worse than that, because as part of your agreement when you are registering for any of this cloud provider, you are giving your IP and all of the results that it could be obtained out of this to these devices. So this issue of privacy is a very important issue. It's not just a matter of, I don't want to share my data. It's just a matter of, imagine you want to discover a drug, and you don't want to necessarily share this knowledge with the provider of the services. And on top of that, there's another problem, not just necessarily maliciousness of the parties, is that these are devices that soon are not going to be classically simulatable, and you're going to run a computation. How do you know this computation is even correct? You get a bunch of numbers on this device, and there is you heard about the NISQ devices, they are noisy. Did I get the right computation or not? So these are the two problems that we're trying to address, to solve them, and once we have a solution, we can put all the building block and goes to the malicious setting. Okay, so the very first result is that, okay, how does this problem solving classically? Classically, surely that's the same problem. People put all of their data on the cloud, and everybody wants to have security and etc. And this has been an open problem in the field for the last 30 years. That can I write somehow, this is the picture. I want to have a limited computer, might be my laptop, to write my computation, to encode it to some encoding Y, such that this encoding is good enough, doesn't leak any information. Then I give my encoding to the server, and server run the computation on this encoding, and out of that encoded outcome, I get my desired function. So it's a very simple problem, and it's called homomorphic encryption, and it's part of it, and it was open for 30 years before Gentry in 2009 actually come with the solution, which is called fully homomorphic encryption, which allow you, in theory, and more these days is now actually in practice, to achieve these magical things that I'm doing encryption, I send it to the server is doing computation, I get back. So this is the classical solution. This is a classical secure solution, and some of the actually devices already in the classical cloud, they provide you this. So now, you would ask, okay, perfect, so let's pick up this wonderful toolkit, this FHE, and try to use that to achieve. And let's assume that because we are going to the quantum era, we want to make sure that everything is quantum safe. So there is a set of results that actually tell you, it depends what you mean by secure access. If you ask the question that, can I have secure classical access to the quantum cloud, there was a bunch of results is that if you want to have information security, i.e. based on no assumption, then you cannot have it even for the classical, and then putting everything together, as you cannot achieve it for quantum, in a very nice link between error correction and quantum, we have that result. Then people started digging into it and said, okay, if the function is a limited function, you cannot also have this, all of these no-go results. And finally, we put everything together in a joint collaboration. We show that, in fact, answer simple, if you want to have information security for the quantum cloud, you cannot do it with a classical communication. So how do we get this really strong no-go result on the impossibility of information security? Like anything in complexity is based on something goes wrong, and that means polynomial hierarchy collapsing at the third level. And we believe this thing is not possible. We believe in polynomial hierarchy, and that's how we catch it. Well, this is not the main topic, but I just want to quickly to give you the feeling is actually this is a work that was built on the classical setting. As usual, we look at what is possible in classical. There is a very nice result by Abadi et al. That they formalize this notion. They say that let's consider you want to calculate some computation in BPP, bounded polynomial computation, and you're asking question, can I put the hardness of this thing on some sort of oracle? I mean, I just encrypt my message and I send it and I carry on classical communication with this oracle, and I want nothing to be leaked about the instance of my problem that is in here, but at the end of the day, I get a computation. And this is very strong link between complexity and cryptography, because they show that actually the only function that could achieve this sort of being able to compute unencrypted without leaking any other information are limited to this complexity class MP intersection, poly, whatever it is, doesn't matter. But bottom line, you can read this slide as saying that, well, it is not the case that any hard problem in NP complete can be sitting in these generalized encryption schemes. So very limited function can sit in here. You cannot always hope that I can do the hard job by some remote server and get the result out of it, unless polynomial hierarchy collapse to the third level. And then, in a short, we extend the same sort of formalism to the quantum setting, said, okay, what if I have this quantum computer? Well, easy problem for quantum computer are not exactly NP, maybe they are inside, maybe they're not. So there was initially a hope that maybe there is a way that I can encode the instance of the problem and I achieve exactly what we want. And we uplifted the same proof technique that exists classically, and the answer is that no. So indeed, if everything that a quantum computer can be doing efficiently could have been hidden in this way that we are saying, then again, polynomial hierarchy collapsed to the third level, almost the same assumption. So we know that is not possible. Although the result is not as strong as we want because it's relative to an oracle, but doesn't matter. Just you can take it for granted of this very quick thing is that if you want to have secure classical access to quantum cloud, it's impossible. You cannot have it with the classical internet. So it's very natural to ask the question, what if I have secure quantum access to quantum computer? I mean, I'm not forced to classically communicate with these quantum devices apart from some scenario, which we can discuss later. So that was exactly the sort of result that we're seeing. So it's okay, let's look at it. So we have a limited quantum client now. Okay, it's not maybe doesn't have fully classical, it has fully classical capacity, but we give a little bit of quantum, not a quantum computer, a little bit of quantum, and we're trying to bootstrap this small quantum client to do the full computation. So now my encryption could be quantum state to quantum state. My encryption could be quantum encryption. I will create quantum link, quantum internet, quantum link that as we said. And then I run my computation on this encrypted quantum state. And out of this encrypted quantum state, I get the outcome. This is a protocol that we introduced in 2009 with Anne Brodman and Joe Fitzsimon. And if you really look at inside, is all the building block that exists. So what is it, this encryption that is very simple and it doesn't need quantum computer? It's QKD. It's the same QKD that is commercially available. So very, very simple encryption is needed. So where the magic comes from, I can do compute on an encrypted state. Well, that's our beloved teleportation that you heard. So using quantum teleportation, you can actually manipulate quantum encryption and make the computation on top of it. And how do I know everything gone correct and nothing has gone? It's the self-testing that, again, we knew it, trying to be able to do some simple tests to make sure everything goes together. So in the next few minutes, 10 minutes, I want to show you all of these things, remind you all of things, put them together to understand its core protocol, then I speed up, because then I just add some more ingredient on top of it to reach to the final goal. So let's take it easy and try to understand how this QKD teleportation testing goes together, okay? And let's start with a very, very simple example. Imagine this magical quantum computation that you want to do. It's a simple gate, you know. These are like, you know, you saw some single qubit gate. They are 2 by 2 unitary metrics. I'm writing this one because it's parameterized by alpha. It's universal for single qubit. It's phase followed by Hadamard. Doesn't matter. So I want a quantum computer to do this thing. So usually, if you remember from lectures, you draw a wire, and then you apply this gate on top of it, and that's how you do quantum computing. So I'm going to show you a little bit of a bizarre way of doing these things, which is called gate teleportation, which are almost wasteful if you think about it, but then later on you see that why is actually the best way of doing computation. So instead of taking one qubit, which is a vector of is a two-dimensional vector, and apply this matrix and to be done with it, I'm saying that, well, take your qubit, add another qubit, apply this 2-qubit gate on it, which is some sort of entangling gate, just in case you didn't see it lecture. Then measure the top qubit, which is now entangled to the second qubit, in this orthonormal basis, which is defined by that parameter, sorry, it should be alpha. And then assume if it's projected to the one, to this vector, which is, this is alpha, or in the other one, you define it 0 or 1. So this dot is a classical control. Based on that outcome, you apply this Pauli X or not. And you sit down and you do calculation quickly in your head. You see that this is exactly what we wanted. It takes this qubit and is applied this J alpha in it. So if I close this as a box in here, for you, you just take this one and you apply your gate on top of it. But in a sense, I open the box because I want you to think outside of the box. And if you think about it, this is a much more modular way of implementing our single qubit gate. So now, why this modular, bringing an extra, doing entanglement, make a measurement, is called gate teleportation? Because in a sense, it's like the teleportation protocol between Alice and Bob. I teleported this qubit from this wire somehow to here. And during this teleportation, I apply my gate on top of it. Why this is useful? Because we are in distributed scenario, because you have this client server. So now imagine you have an Alice who doesn't have quantum computer, doesn't have a qubit, doesn't have a gate, doesn't have the 2-qubit gate, doesn't have a memory, doesn't have any of this fancy stuff, but it still likes to apply this little J alpha gate. And the only thing that she has is single qubit, random single qubit. Well, if you look at this thing, it's if she needs to tell to Bob, could you please create entanglement, do all of these things? But what is the most important value in this structure is just this alpha. So if I somehow hide that alpha that Alice wants to tell to Bob, and yet achieve exactly what I wanted to do, I have achieved the privacy, because the thing of this gadget box that is the private data of Alice is the alpha. And it's very easy to do that, because if you do a little bit of calculation, instead of telling to Alice, to Bob, please make a measurement in the basis alpha, you randomize it. You do one-time path. You take alpha, you add a random theta to it, and you think, well, okay, my computation is completely strong. You know, I rotated it. It's no longer the thing. Bob is thinking that I'm doing J of alpha plus theta. But magic of quantum, because these are all diagonal and this is another diagonal operator, allow you to pre-rotate your state. So essentially, randomize your qubit. So when the actual computation is done, is de-randomizing the computation. So in a sense, I know how I want to introduce noise in my system such that Bob does not know what is doing it, but I send the key in advance and how to decode it. So that little gadget is allowing me to hide the angles. I'm telling Bob to do exactly what I want, but he has no idea what he has done, what I asked him to do. So he thinks that, okay, she's doing some computation with this angle, but in fact, that is not that the angle. The angle is alpha. And the theta cannot be detected out of the system because it's with the QKD part of it. And you can do a little bit of more randomization, you know, because in fact, I don't even want Bob to know the result of my measurement is correct or not. That 0, 1 is, I want to, even that to be one-time padded. and you add the pi rotation, and off you go, you have it. So in this little gadget, I have the building block of making sure Bob does not know what he's doing. And then I need to compose, is the composition. I put all of these things together, and then when you rewrite all of this quantum circuit together, you achieve this universal way of doing hiding computation. And you need to interact because all these measurement angles are linked together. So I'm going a bit quickly on top of these things. But the picture that I want you to have is like back to our normal beloved quantum circuit, if you wish. So I just rewrite all of those things in a simple rewriting rule. So essentially, Alice needs to send a bunch of random single qubit, which is precisely these little quantum things we gave him. And this is we gave her, sorry. These are key. These are random key that she's taking up, sending it to the server. And then quantum computer is going on. Bob is supposed to apply this complicated 2-qubit gate, apply this single qubit measurement, and everything is completely remain hidden. Bob has no clue what is the computation, what's the outcome of the computation, what's happened. This is precisely like the homomorphic encryption in the quantum setting for us. So that's the protocol. So we send a bunch of qubits. Those qubits are the only quantum link that Alice needs to send to Bob. The rest of the computation is that he needs to create entanglement, all of these things together. And after that, there is classical communication. I need to calculate a little modular pi computation of what is my data, how did I encrypt it, how do I add the randomization, tell to the server, please make a measurement, give me the outcome, I do this thing, and this interactively goes. So that's the building block. Obviously, I'm not going to go through the security, but when you go through it, the way that we can prove the server has no information about what has happened is just because we can show all of the communication, both the classical state that we send and the quantum state, are independent from the secret. So you have the secret, which is your particular program, whether it's a machine learning, whether it's a factoring algorithm of something. But this distribution that I send, this bunch of this plus theta state that I send, and those angles, they are independent. Mathematically, you can show that this is like a probability distribution independent. Good. So we achieve blindness. Bob has no clue what I'm doing. It's perfect. That's the QKD and the teleportation part. But what about correctness? So maybe Bob is just receiving this thing and he just produce some random bits and give it to me and charge me. Like in Amazon, you can run so many computations. You have no clue if it's really a quantum computer that is running it, or is some sort of classical simulation of this thing, or is actually completely wrong because the device is so noisy that it gives you a bunch of random bits. So this question of correctness is really, really critical. Even if you don't care about the privacy of the data, you just want to know about the correctness of your computation. And you want to show that you want to have some protocol of accept, reject, that if everything is fine, my device is not so noisy, is really a full quantum computer, is working very well, yeah, go ahead, this result is good, take it. But you also want to have something which is called soundness, that if it's too much noisy and it's too many things are going wrong, well, okay, reject, make me sure that I go, because, the computation goes wrong. So how does this started? This is started, of course, with the wonderful work of Frédéric Magniez, Harold Olivier, Dominique Meyer, and Mike Mosca. They started asking this sort of question already in 2005, thinking, decide somehow this physical device is simulating what it's supposed to do. But that was the beginning of the thing. We were not really facing the actual quantum computer and how they're emerging. And this field by itself is required the whole Collège de France discussing about it. But it has been going. I just not doing justice about many, many people who have introduced many, many different protocols, but just putting it together. Sometimes you have a scenario that you have one single prover and preparing and sending something. There is a bunch of protocols. The important thing is that there are all the time this complexity of communication and computation is keep changing. Then there is another one that you have a server which is preparing things and is sending to you and you're measuring it. Is another family of the protocol coming in here. There is also very similar to the original self-testing. You have two servers which are entangled, but they don't communicate, and you're trying to do some Bell inequality test and etc. to doing it. So this field has been going on and on and on. And there is a lot of result. In fact, there was a very nice set of lecture by Thomas Vidic at IHP, which was exactly on this topic of verification of quantum computing. But for my purpose, remember I said that, oh, I have this data center, things can be done today, right now practical. we needed to move a lot and come up with something that can be done today, rather than with this complexity, which are very good, but they are not allowing you to implement them today. So here's the idea of this very simple protocol that very recently we managed to push them to become super practical. Because most of these protocol, while they do the job, but they almost, the overhead, you're giving them a 100 qubit machine, and out of this 100 qubit machine, you ask another 1,000 to verify that 100 qubit machine. That's not good. We want to have, if Pascal is building a 100 qubit machine, I can verify that 100 qubit machine without asking for another 2,000 qubit to sit on top of it. And they need to be also taking into account the devices are noisy. They are not perfect devices. So you need to be careful about this noise and part of it and the scalability. So here's the solution. We started the work in 2012 with Joe Fitzsimon. The picture is almost the same blindness. So the point is, I'm supposed to do this computation. This is yet another way of drawing the same thing that I was showing you. There is this circuit, the qubit has been sent, server has no idea what the computation is doing, but the fact that he doesn't know what he's doing, I can add tiny little bit of a tiny bit of a test. So what do? I will put this red qubit, which are a randomized QKD state again, this plus theta state, 0 plus e to the I theta 1. And then I put the blue qubit around them to isolate them. So now these red qubits are completely isolated from the rest of computation, and then I can put as many of them I like, be careful about the whole computation goes through. And why this is interesting, because for those red qubits, I know exactly what the outcome is. This is a single qubit measurement, that's the self-testing part, I know if it's preparing the state plus theta, and you're making a measurement in the same basis, the outcome deterministically is either 0 or 1. So I have no clue what is the overall computation, what is 0, 1. For each of these qubits, I don't know what should be the outcome. They are probabilistic. But for this particular red one, they are deterministic. So now we need to develop a theory that says that, well, it's enough just to check this red qubit. If the red qubit gives you the correct outcome, the whole thing is correct. How do we do that? Well, we take advantage that the position of red qubit is unknown, the measurement outcome is unknown, and this beast that it was supposed to be a general noise of my device, I don't know how it's deviating. Does it have a quantum computer? Can it entangle? Is it really take my qubit or send it out? All of this general, completely positive trace preserving map, which is a beast that it can happen in a general, will be reduced because of our security, because of our hiding technique, to a bunch of very, very simple tests, which we call in the test subspace. For those test subspace, we have this deterministic computation, and then the theorem goes something like that, that we will show that the probability that your test is correct, but the rest of computation, almost orthogonal to what you wanted to see, is bounded. So this is now like a little calculation. You need to put, we didn't go through density operator, etc., but it's just like you look at whatever deviation that has happened, then you define this bad scenario that the outcome is orthogonal. It didn't give me the quantum outcome I want, and yet my traps give me correct. Well, we proved to you, according to the result, that this is very unlikely. So, and this epsilon is exactly dependent on the noise of your system, how many traps you put, what sort of computation you're getting it. So this was the technique that we developed, but still the overhead was really, really high. And I was very happy. The same guy who started the self-testing joined the team, and now we can claim that we actually got our dream job. We have something that is robust and is working for the NISCI devices, and the idea of it is that, well, you just need to have a little quantum computation that you have. Let's say this is your quantum chemistry problem that you want to simulate. You have no idea if it's correct or not. You just run over and over. You don't ask more quantum computer. You don't ask more qubit. You take the same 100 qubit that is provided. You run several rounds. You keep repeating. Some of the rounds are the testing. Some of the rounds are the computation. The computer does not know when I'm testing or when I'm computing. And putting all of these things together, we have this protocol that works for classical input, classical output, which is fine, because most of the thing we do with quantum computer, we just want to run some sampling problem. It works in the exponential regime, means that I really have the highest level of confidence about the outcome. And it's also, if your device is honest, it's not a malicious device, it's not somebody who doesn't have quantum computer but wants to sell it, but it's just a bit noisy. And you don't mind because in most of these applications, we are happy to have a bit of error. We saw that in many of the applications as well. Well, it's going to work. It's fine. I can tune all of these parameters. So essentially, the message is that, good, the first building block, a verifiable, blind, honest client, malicious server, we have it. It's ready. It can go and discuss about how we can implement it. And in fact, this is the blueprint of Quantum Internet Alliance that was built out. So this is part of that project that this is about to be demonstrated and showing that even over, I know, ideally maybe a few kilometers, you can have a verifier which has only a single qubit and actually really run a mini quantum computation and making sure that it's correctly done with taking a noise. Okay, so now it goes to the rest of the talk. Okay, so we take care of this one honest client, but oh, maybe before I go, I slightly cheated when I said that it's impossible. Oh, no, secure classical access to quantum cloud is impossible, just to keep my story true. It is really not impossible. So in fact, if you're happy to reduce your security requirement to be computationally secure, more precisely to be post-quantum safe, classical access to quantum cloud, that is something is possible in theory. There was a very nice breakthrough in the field that their classical FHE that I was showing you at the beginning can be manipulated and be adopted in order to allow you to do secure computation. This is a result by Urmila Madhav. And similar to that, in a little bit of a different approach, we also adopted it in another work. And the idea of it is like, you take the same blind protocol that I was showing, which part is quantum? Well, it seems this is the only part that's a quantum, and it's very simple. It's just sending single random qubit. And then you can pick up the LWE-based post-quantum secure classical encryption that it somehow almost gives you the same randomization that the single qubit gives. Seems to be too good to be true, and in fact, the problem is that it's about the numbers. You need order of 1,000 server qubit to create the randomization that is comes from one single qubit of client. So in theory, it is possible to have secure classical access to the quantum cloud. But in practice, we need to wait till the qubits are so free and we have this universal quantum computer with millions of qubits to ever go down that route. So that's why we are sticking to the route of we need to have quantum communication because the one single qubit versus 1,000 qubit is something that we cannot afford right now. So in short, I'm going to claim a theorem that the secure access to quantum cloud is equal to quantum communication. So because it's the most efficient way of doing things. And so we need to link this in pocket. Okay, so good. So this is the first part of the thing. But now we start to gear it up. We're going to say that what if my client is not so honest in the sense that, I can access to quantum Amazon, and then later on I need to pay for the service, and Amazon is happy to do it in a blind fashion. But later on I say, well, no, Amazon didn't do right computation. I'm not going to pay you the price. If it's supposed to be a service, you need to also protect the business of the cloud provider. So you need to now take into account that maybe my client is also malicious, and my server is malicious, and maybe each one of them have computation. Maybe I'm the Google, I have a quantum Google, I have a bunch of database, and I want to collaborate with the Amazon, which is a bunch of other database, and off we go. We want to do this sort of computation. And in this scenario, it's very similar to the Yao protocol that you have been here. It's really two-party quantum computation. So the idea is that, okay, we know one technique. We have this little QKD state. We are sending it, and we just now need to take care of the fact that the server should be able also to test the client. Before, in the previous example of the secure cloud that I was showing, the client was the good guy, was definitely doing what he's supposed to do, so we didn't take care of any tests to be doing on that side. Now we need to do almost the same self-testing that we do for the quantum server. We need to do some testing for the client and making sure that everybody playing according to the rules. So that's what we need to do. The protocol is really like the classical Yao-Garbo circuit. So in the Yao-Garbo circuit, you encoding your computation, even though that everybody knows what the circuit is. And then Alice sends this garbled circuit to the server, and then the second party or the evaluator is getting the information using, here's the only thing is, it doesn't matter the protocol. The point is you're using a building block, which is oblivious transfer, in order to create these bigger blocks. So you're using the simple thing to give you that. And off you go in quantum, we do exactly the same thing. So we send our beloved single qubit. They are the same little QKD state that we're sending it. The server is supposed to do this complicated putting things together, etc. And then we're almost using a same sort of classical SMPC for computing the evaluation to push everything up. So off we go. So everything goes together. But the problem is that so far, this is exactly like the classical YAO. It works if the client is not too much cheating. It's what's called honest but curious, in the sense that the client is not completely putting some other computation, trying to get the secret data of the bulb. So again, we look what is exists in the classical world. How did people add the verification to the classical YAO? And that's what something is called, oh, sorry, my slide is not coming in animation, but there is something that it calls boosting the security, cut and choose. So we are sending a bunch of this plus theta state. Well, we send a little bit more than usual, and the server first is checking if the client really sending plus theta. Maybe he's sending entangled state. Maybe he's trying to do some sort of other state. So the cut and choose means I send you a bunch of qubit. You, as a server who don't trust me, choose some of them. I prove to you they're really exactly plus theta. They're not entangled. It's precisely what I'm saying. And once you're convinced with my proof, then you start running the computation on the rest. So what is funny about this protocol is that this cut and choose technique only works if the state that you send from client was all of this single state. So somehow in my story, I motivated that, oh, the client needs to be minimal because we don't have quantum computer for everybody. So this data center, everybody needs to have just a simple QKD. But in fact, this is the only type of state you can do this boosting on top of it. So we have a practical, efficient, malicious client, malicious server, but it again is proving that it's very rewarding to keep what the client needs to do, what party are doing it to very, very simple. So again, it's a very nice example of why delegated is the right way. Okay, cool. Oh, I'm going pretty fast, so I can go now, slow down finally. Any question in the middle? No, I'm not supposed to ask. You're not supposed to ask that question. So let's put it together. So far what I have shown you. So we have this blind computing, which was QKD plus teleportation. We add some sort of testing. And now, finally, I go to the multi-party scenario, which is the whole point of, somebody has quantum algorithm. That's, I don't know, is like Microsoft coming with the algorithm. Somebody has quantum computer, is Pascal, Google, etc. have a computer. Somebody has actual data, is a bank, financial bank, they want to run some quantum machine learning in this distributed way. So this is exactly, we are back to the target. So you think that, okay, let's put everything together. It's fine. How difficult it is. You have a bunch of people. Again, they send a bunch of their QKD state. The QKD state comes in the middle. And now, instead of one state being randomized with the key, well, they need to do some sort of collaborative key creation. So I have my own randomization key, which is in here. This is some other party randomization key in here. And now the server needs to mix it. It's a little bit like secret sharing protocol. I have part of the key. Somebody else has part of the key. Collectively, we're creating this key, which everybody has put the party in it, which seems to be the right direction. So I contribute my key, you contribute your key, and again, we're bringing this computation, teleportation, all of these things that we saw before, verifiable things all together. And okay, I put some key in this masking, you put some key, and now we want to tell the server what to do computation. How do we do it? Well, we use classical SMPC to collectively do this calculation. It's the same type of calculation. My angle, what's the randomization, etc. And seems everything goes well, very well, no? And indeed, everything goes very well, apart from when we sit down and write the proof, we realize that we need to impose a very strong assumption that although the client could be malicious and they don't trust each other, they don't want to share, and the server itself could be malicious because maybe it doesn't have quantum computer, etc., but they need to not collude with each other. And we kind of like, we said, well, no, it's just a matter of, like my postdoc, Anna, by then if she wanted to finish the paper, we said, okay, we write it and surely it's a little bug and later on we can fix it, And that was in 2007 and we were stuck with that bug. Somehow when we went to this multi-party scenario, this non-colluding, it was something, we could not get rid of it for a long, long time. And the reason is very interesting. This time, the simplicity that I was imposing that, oh, let's everybody just have QKD is very nice. We don't want everybody to have quantum computer and everybody send everything to a one quantum server. That is the part that it was actually firing back. Because I need to do verification or self-testing of a not trusted server. So I need to put trap. Remember those trap that I was putting this? So I'm inserting a trap to a part of computation that I'm in charge. But I'm doing some sort of broken pieces, which I don't know what the other people are doing. And we need to make sure when I'm putting trap, and Fred is putting trap, and somebody else putting trap, those broken pieces can come together, and I still have a path to do computation. But how do I know where did you put the trap so we can come things together? Because otherwise, I need to tell Fred, can you please tell me where did you put your trap so I make sure that my trap is compatible with yours, and off we go. So it's no longer possible. We want information from each other, but we don't want information from each other. So we're somehow stuck. And there's this very nice result came in 2020 by a colleague from Leipzig and QSoft, that in the case of symmetric, now they said, okay, let's assume everybody has quantum computer. It's not anymore just about one quantum computer. They resolved this problem that, okay, because now I have my quantum computer, I'm running my encryption, decryption on my side, then I give it back to you, you do your encryption, decryption on your side, and things work out well, and they have exactly this quantum secure multi-party protocol. But it was not really what we wanted, because then we need to have 1,000 quantum Google that everybody is connected together, and that's not happening tomorrow, at least. So we got a lot of inspiration from this work, and we realized that actually the trick is, again, Harold is showing up here. The trick is that you always need somebody fresh mind is coming in. Okay, we need to do a little bit of more work. Okay, fine that, I don't know where Fred put his trap, and I don't know where somebody else put the trap, but we can ask more out of our secure multi-party computation from our classical part. So let's make sure nobody knows anything, and whenever they want to coordinate with each other, we go back to the classical SMPC. So that was the sort of changing that all those bottlenecks that we were saying is not possible, I need to know, but I don't need to know. These are all classical information. So the simplicity, so the message that I'm repeating again here is that the simplicity of saying that I just send QKD, everything is done by the teleportation, the rest of computation is only classical. Well, so use classical SMPC to resolve all of your problem, and that's exactly what we do. Then, of course, so essentially what is now we invented is like a double blind computation. It means that not even the client knows what's going on. Not only the server knows what's going on. Nobody knows what's going on. There is this SMPC box that is orchestrating. So you essentially have an orchestrator which is exactly tell how things need to come together. So maybe in the picture it becomes better that in the previous set of the beginning of the seminar, I was showing, okay, the client knows what's going on, send a bunch of qubits to the server, and is orchestrating what the server should do. Well, okay, now let's put a trusted third party for a second, a trusted third party that instead of I tell exactly what the server should do, I tell to this trusted third party that please indicate what measurement should be done. Please indicate what correction needs to be done. And now this part and the beauty of this client server is that trusted third parties only need to do the classical computation. So I can plug a classical SMPC to do precisely the job of coordination and putting things together. So, of course, along the way, you need to completely rechange your proof technique and etc. But if you have a good collaborator, they take care of all of that. So the point is that now everything is orchestrated with a classical SMPC. These malicious people collaboratively preparing a bunch of qubits. They could be not the right qubit. They could be the right qubit. But we also know that it's okay. We can let them to maliciously deviate because later on they cannot directly attack and try to get the information because they need to go via SMPC, and this SMPC is trusted. So as long as my classical SMPC is trusted, my whole computation goes through correct credit. So that's exactly. So the main idea is that before the client was sending the trap, was sending a dummy, was sending the computation, but now even that part is blindly done. And this is the part that, I don't know exactly where my trap is sitting. I don't know where exactly my computation is sitting, and that's good for me because then I can recover everything. And the only thing is I want you to say, like, okay, by doing it in this sort of client server, we get the best communication complexity, etc. So maybe compared to all the other nice work that is very active, many people are putting, is that we only need to, which part I want to show you, that we only need to have one fault-tolerant quantum computer. We're back to the message. You want to do quantum secure multi-party computing, one quantum computer is enough. You take that one, everybody else with the QKD link is connecting to that, and they can run the whole quantum computation for this problem, off we go. And we have communication, etc. So now you would ask, am I done and dusted? Can I put a tick box that also the efficient malicious client, malicious server solved? Well, not really. I mean, these are the results that is coming only over the last few months. So there is a huge place to optimize them further, but they are very modular. The construction that I'm hoping that you followed a little bit, we'll do a bit of UBQC, a bit of SMPC here, a bit of testing in here, they are separated. So if I improve my SMPC, classical SMPC, to be the right post-quantum secure for calculating this angle, I plug that into place. If I look at my remote state preparation, which is the most important part, and I somehow come up with the most efficient way of implementing, well, good, you plug that one into the picture. This blindness, do I really need to hide every single qubit? Maybe there's only few of them are the important parameter. And so hence I apply less of this hiding again to picture. So this is an ongoing work. So we cannot really say that we have the completely practical one. But there is one thing that is very, very important in all of this thing is that no matter how the theory work is improving, the engineering part, I like to call it engineering, is reduced to just a very simple thing, which is this remote state preparation. Okay, so of course I can improve my verification protocol, my blindness protocol, my SMPC, but the only part that will need to be today to be resolved, and hence claim that we are going towards the implementing in this remote state preparation, which is essentially how do I send the qubit inside some device? And that's what I probably finish up in the next 5 minutes to get a little bit of perspective that why we're excited. Because we know exactly this building block gives me blind computing, verifiable computing, multi-party computing, etc. So let's dig into this result that everybody put their random key. So you have a bunch of party that they need to put their random key, but this random key is a very simple state. It's just a single qubit state. And then collectively you need to build this randomized state which is coming out of the key. So in a very recent work together with the colleague from VeriCloud, Mark Kaplan, which is the co-founder, and the other student, we actually dig more into it, and we realize even QKD state are not required. You don't even need to really have the full plus theta. You just need to have random rotation. So there is something that now we realize, which we call it remote state rotation. The only thing that you need to give to your client is just to be able to do some random rotation. They don't need to even have a single photon source to prepare a state. They don't need to have any complicated operator compared to all the things you say. They just need to have something is called random remote state rotation. And one thing that I didn't say to during all of my talk is that presenting everything is very easy. You change here, is modular, and yet everything remains secure because the students are taking the pain of proving everything in this universal composable framework. So I can tell these stories. They are much harder to be proven, but all those components written in this bizarre picture is that there is a very nice framework of universal composability, abstract crypto, which allow us every time we do a security proof for this little function, and we know that things are plugged together. So that's underlying picture of all of these things. But now, the grand final part, which allow me to a little bit advertise about VeriCloud, and then our belief that the exactly verifiable quantum cloud in the multi-party scenario is something that we can deliver today, is that VeriCloud has put forward a new architecture, which is effectively looking at all the communication and all the sort of QKD link that you wanted to achieve in a very, very simple way. It's not a solution for the, on the satellite distance if you want to connect continents together, but if you're talking about the various parties which are in the 100 kilometers from each other, which is usually the case of your data center, then you only need to have one single quantum computer sitting here, one single source sitting here, all of these other parties doing this remote state rotation that I was talking about, and now everything goes together. Take the quantum SMPC that I was showing you, take this remote state rotation that I was showing in the previous slide, take this Q-line architecture together, and that's something that we are hoping that in the next few years we actually can show demonstration of it. So if you have few nodes that they want to do this sort of data center link together, is something that we can provide. So I guess that's it, I can claim that we are entering a secure new world. We can connect everything. We can put quantum computer together. We can put quantum link together. And we can achieve something that is not possible classically in terms of this enhanced security verifiability. So maybe I stop there if you have any other question. Thank you very much.